Okay, welcome to the webinar. I am very pleased to introduce your chair for this session. So it's Dr. Claudia Antolini, who is a science communicator. Over to you.
Good afternoon, everyone. It's a pleasure to be chairing this webinar today. This is the Tiger in STEM summer webinar series. And today we have two great speakers from really the frontiers of physics. So today we have two great speakers from the frontiers of physics. We have Claire Malone that will talk to us about the standard model of particle physics, and we have Cheyenne Polius that will tell us everything about heavy elements and how supernovae may have contributed to the birth of life on Earth. So just to remind everyone, this series of webinars is being run in the memory of the late Canadian-American geophysicist and planetary scientist Claudia Alexander, whose work and leadership paved the way for many of NASA's missions, including the Galileo mission. As a Black woman, she reached the very top of her disciplines in physics. She was a great role model and has left behind a legacy which inspires many even today, especially women of color working in science, technology, engineering, and mathematics. In celebration of her contributions to science and the recognition of the immense work that still needs to be done to support, we request that attendees of the webinar consider making a donation to the charity Generating Genius, which is a London-based charity helping school students from disadvantaged backgrounds, particularly Black and Black minority ethnic students, to enter university and enterprise careers in STEM. You'll find the link below in the YouTube description. You need to scroll down. So without any further ado, I would like to introduce the first speaker for today, who is Claire Malone. And the title of her webinar is Fixing the Standard Model, Pairing of Particles. Some background about Claire. Claire completed her Master of Science at Imperial College London. She is now completing her PhD at the University of Cambridge in Churchill College. She has conducted a portion of her research at CERN. She takes all of her work to an assistant due to her physical disability, cerebral palsy. She's very passionate about improving the environment for LGBT people in STEM.
Hello, everybody. I am a member of the High Energy Physics Group at the Cavendish Laboratory at Cambridge University, searching for new particles using the Large Hadron Collider, LHC, at the European Organization for Nuclear Research, SLR. Today I would like to show you how finding partners for fundamental particles could solve some of the biggest problems in our field. But first, a little about me. At school, I was the archetypal geeky kid, wanting to just get the other lessons out the way, so I could get into the science labs. After school, I went to Imperial College in London, and graduated from there with an MSc in Physics in 2014. That's a photo of me on my graduation day, and it is clear evidence of the fact that, if you do too much physics, your hair turns purple, so be warned. I have almost completed my PhD, sometimes working at SLR. Some of you may have seen it on the news, a few years ago, when they discovered the Higgs boson. If you haven't, maybe go and check it out. I have also been various shades of queer, and have been actively involved with the LGBT societies at Imperial, Cambridge, and SLR. I have currently settled on being pansexual with she/her pronouns. I have generally had a good experience of being LGBTQ in STEM, mainly because each institution I have studied at has had an active and friendly LGBTQ society. However, my physical disability has had a much greater impact on my career as I generally dictate all my work to an assistant. The idea of dictating equations and code may sound strange if you have never had to do it before, but if you have been doing it throughout your education, you find techniques to make it work. I also completed lab work by giving very detailed instructions to my assistants about how to use the equipment. For example, if we look at the experimental setup of our friend in the left-hand cartoon, to express how to place the spring on the hook, I would say something like, take the spring that is approximately 8 centimeters long, attach the weight that you have measured to be 247 grams to the end of the spring that has a big hook, attach the other end of the spring to the stand. A small complication with this is that I was having to describe things that I had never physically done with my own hands. To get round this, my assistant and I met outside school hours to practice how I was going to dictate my practical exam. To begin with, he would go through the steps of setting up and performing the experiment whilst verbalizing what doing, such as, I am taking the spring that is approximately 8 centimeters long, etc. In a way, I thought of him more like a dance partner than a laboratory assistant. I was learning what I needed to say to make the experiment happen. When I had got an idea of how I was going to explain how to perform a variety of experiments verbally, we practiced with me giving the instructions. During this stage he did not speak at all except to state if he didn't understand an instruction. I guess at this stage, although it may sound weird, but I had to stop thinking of him as a person and start thinking of him as a part of the equipment that I needed to use to do the experiment. Before and after the experiment, of course, I thought of him as a person, my assistant and friend who I got on well with. The framework that describes the behavior of the particles which high-energy physicists study is called the Standard Model of Particle Physics, or STEMM for short. The STEMM describes fermions, which are the particles that comprise matter, and bosons, which are fundamental force carriers that mediate the interactions of the fermions. Fermions are divided into quarks and leptons and are arranged in 3 groups called generations. So, as shown on the slide, the first generation would consist of the up quark, down quark, electron, neutrino and electron. The particles in each successive generation have higher masses than those in the previous one. The bosons of the STEMM mediate the fundamental forces that act on the fermions, photons for the electromagnetic, EM, force, W plus or minus and Z for the weak force and gluons for the strong force. The EM force governs the interactions between electrically charged particles via photon exchange, while the weak force can transform one lepton or quark into another, provided it is in the same generation. This is the force responsible for radioactive decay. The strong force is responsible for transformations between different quarks and is the force that holds protons and neutrons together. One of the particles you may have heard of is the famous Higgs boson. The particle gained its illustrious reputation by escaping detection for the longest, until its discovery in 2012 etc. The discovery of the Higgs boson is crucial because it provides the mechanism through which all the other particles attain their masses, even though the more fitness-conscious particles may disapprove of its activities. The STEMM even has a child-friendly version, in the form of soft toys for each of the particles. Some of these particles, many of you will be very familiar with. The protons and neutrons in the nuclei of atoms are comprised of up and down quarks. The nuclei of atoms are orbited by electrons, which play an essential role in many physical phenomena such as electricity, magnetism, and chemical bonds. Photons are the quanta of the electromagnetic field which is responsible for all EM radiation. However, other SM particles may be less familiar even though they are around us all the time and in some cases crucial to everyday life. It would be pretty tricky, or impossible, to form protons and neutrons and hence atoms without the gluons holding the quarks together. Gluons are, of course, not to be confused with the warlike humanoid alien species from Star Trek. Life as we know it would also not exist if nucleosynthesis in the Sun did not fuse hydrogen into helium and other heavier elements. However, despite this coherent picture, the SM does not provide us with a complete description of the particle content of the universe. It actually only provides a description of just 5% of the universe, having nothing to add about the remaining 95%. It is one of the main aims of the LHC to remedy this major shortcoming. So how do we know that most of the universe is unaccounted for? We know the observed rotational velocities of galaxies alone suggest that the total mass of the galaxy is far greater than can be accounted for by just the luminous matter. This missing mass has been termed dark matter, and is predicted to account for 23% of the energy matter density of the universe. The SM can offer no suitable explanation as to the character of this dark matter. In addition to this, the unexpected discovery that the expansion of the universe is accelerating, rather than decelerating due to gravitational attraction, points to the existence of a previously undiscovered force acting against gravity on a universal scale. This force, which accounts for the remaining 72% of the energy density of the universe, and is now known as dark energy, also has no explanation within the SM. The SM also does not explain why the universe is dominated by matter particles, rather than containing equal amounts of matter and antimatter. Finally, there is a gap of 32 orders of magnitude between the largest and smallest scales in the SM, which seems quite unnatural. A possible solution to some of the ailments of the SM is offered by Susie. Susie is now one of the strongest candidates for the explanation of physics which is not accounted for by the SM. Susie extends the SM by postulating a supersymmetric particle for every SM particle. These particles possess identical quantum numbers to their SM counterparts, except for a half-unit difference in spin. They also have, in the true tradition of particle physics, very silly names. In honor of the name supersymmetry, a supersymmetric particle becomes a sparticle. The supersymmetric top becomes a stop. For reasons I shall explain, I am particularly interested in finding the stop quark. But how can these so-called sparticles solve the problems we've found? Well, remember we said that we were missing a load of dark matter that is meant to be floating about in galaxies, keeping their rotational velocity constant with the distance from the center as is observed. We hope that the particles could be what this dark matter is made of. But if dark matter is made up of particles, it must mean they are really difficult to detect, otherwise astronomers would have spotted dark matter before now. Also, the fact that they have not been found by such sophisticated experiments like the LHC would suggest that they don't interact with our detectors like normal particles do. In fact, this is what we are counting on when we search for particles at the LHC. We know that conservation of momentum must hold for every particle decay, otherwise something is really wrong, and we may as well go to the pub. So, if we don't detect enough energy from the products of the decay, that must mean that the particles have stolen it, and not been detected. I said that I was particularly interested in finding the top's partner, the stop, and on the slide you can see a diagram of a stop decaying to a top, after the protons have collided at the LHC. The particle on the right-hand side of the diagram is called a utrilio. As she is the lightest particle, so decay chains stop when she is produced. She is often named as a suitable candidate for dark matter. The stop quark has a special role to play amongst the squarks. I mentioned that there are 32 orders of magnitude between the biggest and the smallest energy scales in the standard model. As a consequence, there is no explanation of why the observed Higgs mass is much smaller than the value we would theoretically expect. The mass of the Higgs can be thought of as the sum of the masses of all the other particles, and the top quark has the biggest contribution to this sum because of its large mass. This is where Susie comes to the rescue. When we consider all the particles, as well as particles, we find that their contributions to the Higgs cancel out the contributions of the particles, to leave a nice, light Higgs. As the top is the heaviest particle, the top and the stop have the biggest contribution to make to this cancellation. We can think of that as a tug of war between Susie and the standard model. The SM wants to pull the Higgs mass way higher than the mass we observe, but luckily Susie is there to keep everything in balance. This is why, if physicists can discover the stop and other particles at SLR, it would be very exciting, both from the point of view of finding a description of dark matter, and also explaining why the Higgs is allowed to be so light. So why do I spend my life looking for hypothetical particles that don't interact with any of our detectors? Well, certainly for me at least, the prospect of finally having a complete picture of the universe, in terms of its fundamental building blocks, is more than enough motivation. Or it could be just to justify adding a cuddly toy universe to our particle toy box. Thank you for listening.
Thank you very much, Claire, for a very, very interesting and fun talk. We have received a couple questions in the chat, and I encourage people to please keep posting your questions. I apologize because we are having an issue with captions. I believe that we are trying to use a transcript service at the moment, but we will upload full captions to the video as soon as we manage, as soon as it's over. So we apologize and thank you very much for bearing with us. I'm going to start with the first question that we have for Claire from Rachel Oliver, Professor Rachel. I'm just going to share, okay. So Rachel asked, how did they discover that the expansion of the universe is accelerating?
They looked at the redshift of galaxies.
And they found that the galaxies that are far away are moving faster
And they found that the galaxies that are further away are moving faster
away from us.
away from us.
You, Claire. Then there's another question for Charlotte Cochard. Is there actually a chance to understand the universe with finding the sparticles, so the supersymmetric partners, or is it just an infinite problem?
Well, if we can find the name of Mars, we would definitely know more about the universe.
If we could find the nature of the mismatch, missing mass, we could find out the
More about the
we
universe.
could find out more about the universe.
But supersymmetry is only one theory. So what will missing mass could be?
But supersymmetry is just one of the theories for what the missing mass could be.
I mean, we can't really claim to understand the universe if we don't know what most of it makes of.
We can't really claim that we understand the universe if we don't know what most of it is made of.
Thank you, Claire. We have another question from Liam Rooney. With the current hypothesis surrounding dark matter, do researchers think that dark matter could form macroscopic dark objects, or would dark matter purely exist as a subatomic particle?
There are theories that support both ideas.
There are theories that support both ideas.
From one theological landscape in this area is quite wide.
The phenomenological landscape in this area is quite wide.
And I think what the theory is waiting for is for the data to support any of the theories.
What the field is waiting for is for the data to support any of the theories.
Until it does, we have no reason to dismiss any of them.
Until it does, we have no reason to dismiss any of the theories.
We have next question from Julie Umulige. So sorry if I have mispronounced your name. What are the practical implications of the SUSY model? Would it possibly affect space travel? Oh, I would love to know that.
I don't think we know enough about parameters to really say.
I don't think we know enough about the parameters to really say.
Because if AI tells the phenomenological models, there are many parameters.
Because in a lot of the phenomenological models, there are many free parameters.
And the mass is one. If the mass is about a TeV of the particle, it would have a very different behavior.
If the mass is about 1 TeV of this particle, it would have a very different behavior.
Compared to if it was 5 TeV.
Compared to if it was 5 TeV.
Thank you very much. We have now a question from Olivier Luz. Thank you for your talk, Claire. You mentioned that the missing particles might not interact with our detectors, but then how would we go about detecting them? Or am I missing something?
We detect through the presence of missing mass.
We detect them through the presence of missing mass.
And it shows on slide 12.
Like it shows on slide 12.
If we know the energy of what we put in and the energy of the decay products and not the same.
If we know that the energy, if you know that there's a mismatch between the energy we put in and the energy of the products, then we can detect it.
Then that's broken conservation of energy.
Because otherwise it would be a broken conservation of energy.
And you can also tell by looking at the distribution of what we can see to tell what is missing.
You can also say from the distribution of what we can see, you can say what is missing.
We have one last question from Izzy. If you would like to share your thoughts about how we could boost the visibility and participation of LGBTQ+ colleagues in physics, and from myself, I will add also how to boost visibility of disabled scientists.
Two different questions.
I think these are two different questions.
Yes, they are definitely two different questions, sorry.
more advanced like this help and more networks in universities.
For the LGBT visibility, events like this help, and also more networks like this one will help,
In university,
particularly in university.
for scientists with disabilities, I think first you need to go back to way before university level.
I think for scientists with a disability, you have to go back to before university level.
Because so few get to school aren't enough to form a network.
Because there are so few that get through the school that there aren't enough to form a network.
You need to help parents and teachers to know how to support disabled students.
You need to show parents and teachers how to support disabled students.
Otherwise, they will just drop out.
Otherwise, they will just drop out.
This was an amazing talk, Claire, and thank you for answering so many questions for us. Now we're going to move on to the next speaker for the day. Thank you again, Claire, really from comments in the chat were really saying that your talk was awesome. It was a pleasure for us to have you. The next speaker for today is Cheyenne Polius, and her talk title is How Star Explosions Might Have Helped the Development of Life on Earth. A bit of background about Cheyenne. Her passion for astrophysics dates back from when she was 15. And in 2015, she moved from St. Lucia to the United Kingdom to follow that dream. She has just recently graduated with a Master of Science in Astrophysics from Sheffield University. And it turns out that the only thing she loves more than space is to talk to people about space. So to allow for this, she has pursued a number of activities also on social media. And she was elected as the national point of contact for St. Lucia in the Space Generation Advisory Council, which is a global organization partnered with the United Nations to give students and young people a voice in the space sector. So essentially, she is liaising between St. Lucian citizens and the wider Space Generation Advisory Council. And she raises awareness for the benefits of space technology to St. Lucia and the rest of the Caribbean region. Also, she has founded first National Astronomy Association in St. Lucia, which is called LUNAA. And she would like to use that to encourage space enthusiasts to connect and form a national platform to raise awareness, again, of the benefits of space technology to the Caribbean area. And she has a specific interest in increasing Caribbean representation in the space sector, as well as increasing ethnic and gender diversity in STEM.
So as Claudia mentioned, I'm going to be talking about how star explosions may have helped the development of life on Earth, which is just a more fun way of saying my master's project, and walk you step by step into kind of the background, into why the research is important, and what I had to do to kind of get my results. So I was part of a really amazing team. My project partners were Miti Patel and Matt Risdale-Smith. And my project supervisor was Dr. Richard Parker from the University of Sheffield. It was definitely a team effort, and I'm just happy I could be presenting on some of our results today. So scientists who study meteorites, they found that there's magnesium-26 and nickel-60 in some of the oldest meteorites in our solar system. So some of the first bodies ever created in our solar system have crashed into Earth, and they found them, they've studied them, and they found those two elements in it. And what does that mean for us? Well, these two elements are what they call daughter products of short-lived radioactive isotopes, or SLRs for short. And these two SLRs are Aluminium-26 and Iron-60. So what the magnesium and the nickel that they find now show that it shows that in our early solar system that there was Aluminium-26, which decayed into magnesium-26, and then there was Iron-60, which decayed into nickel-60. So what we find now is the magnesium and the nickel, but based off of how much magnesium and nickel we find and how they're distributed throughout the meteorites, we know that they had to have come from aluminum and iron and decayed rather than just been there. Like there must have been like an external source. So these short-lived radioactive isotopes are called short-lived because they have short half-lives. They have half-lives of a few million years, which is very short on astronomical timescales. So they could be anywhere from 100,000 years to 100 million years. And that's really short on astronomical timescales because when you think about it, our solar system is 4.5 billion years old. Our universe is almost 14 billion years old. So a few million years isn't really that long. So that's what they call short-lived radioisotopes. And because they're short-lived, and because we find evidence of them in meteorites, we know that our solar system had to have had them very early on. So when the solar system looked a bit like this, rather than all the pictures we see with all of our planets and stuff. So it was just a baby sun and a huge disk of gas and dust around it. And astronomers believe that that's when the SLRs had to have gotten into our solar system to produce some of the meteorites that we see today. So it had to have been very early on, before planets and moons and everything formed. So very early on in a star's life, it is most likely to be a lot closer to other stars. So stars are formed in groups. You've probably heard of clusters, star clusters. In the astronomy world, I say star forming region because cluster has its own definition. So I'll use the word star forming region for this presentation, but really just star clusters. Stars are born in clusters. And so, right, so in the first few million years of a star's life, it's most likely to be a lot closer to other stars. And these clusters can have anywhere from tens to hundreds to thousands of stars. And any stars that are more than 8 times the mass of the sun explode as a supernova when it dies. And it's just this huge explosion, and all of the material in the star gets pushed out and spread out into space. And what is made in massive stars? Aluminium-26 and Iron-60. So there's a chance that supernova explosions in the past could have been what enriched our solar system with Aluminium-26 and Iron-60. So my research, there are other theories, but this was the one theory that my research explored, and it's called the disk enrichment or disk pollution theory. So yeah, it's basically saying that when the sun was a lot younger, so the first few million years of its life, it was a lot closer, so it was next to stars in its cluster. And if it was nearby a supernova, when a supernova exploded, then these SLRs could have come from the supernova into our disk of gas and dust and then been incorporated into all of the moons and the planets and all of the stuff we see in our very pretty solar system images that we see now. So what did I actually do for this project? Well, I analyzed simulations of star forming regions or star clusters, and there were two main types of regions. So there's supervirial, which is expanding, or subvirial, which is collapsing. I'm going to say expanding and collapsing for the rest of the presentation because even I got confused with supervirial and subvirial. Like, try writing a 10,000 word dissertation and have to like type words that are so close but completely opposite in meaning. So I'm going to say expanding and collapsing just for my sake and for yours. So star clusters do very interesting things. They can, as you can see on the left, they start out just being a group of stars. All of these clusters have 1,500 stars. And the red dots are the massive stars, so any stars that are more than 10 times the mass of the sun. And the blue dots are all the other stars in the cluster. So if you look at the top panel, you can see that we analyzed these simulations over 10 million years. And the top panel, you can see that the cluster expanded. So, well, the region expanded. So we have, in the beginning, we have 5 million years, so halfway through, and then 10 million years. And all the stars are just moving further, drifting further and further away from each other. Then the bottom panel is the complete opposite, so that as time goes by, the region actually gets a lot smaller and the stars end up getting a lot closer together. So what my job was to track the distances between all of the stars in the cluster over the 10 million years, and we did that with Python. So these simulations had the masses of the stars and their coordinates, so we could track where each star was over the 10 million year time span of the simulation. And that way, when a supernova goes off, so we know which stars turn into supernova, like the simulation includes that data as well. So when a supernova goes off, we know exactly where every single star is, and then we can calculate the amount of material that the sun-like stars get from the supernova explosion. So we looked at stars less than 3 solar masses just because we're trying to see if we could figure, because we're trying to figure out how our solar system got it. So our sun is 1 solar mass. So we looked at stars 3 solar masses or less to see what they would be doing in the cluster and how much enrichment they would get over that 10 million years. So 1 second, sorry, slides not, it's not changing. Okay, so yes, we know, oh, okay, it's fine. So we know where each star is at any point in the simulation. And that was also very useful for taking into account what we call photoevaporation. And massive stars, throughout their life, they just release material that we call stellar winds. And that material it's stellar material. So it's hot and it heats up the gas in disks, and that can cause the gas to escape. So disks can actually lose gas. So we took that into account into the research as well, because we could have a sun-like star that's close to massive stars, so it gets that level of enrichment, but it's so close to the massive stars that the radiation from the stars just causes all of the gas in its disk to evaporate or to escape from the disk, and then the disk is left with not very much gas left. And that's not good for our solar system, because we know our solar system had to have had gas, because Jupiter and Saturn are huge gas planets. So, and as well as the other massive planets also have gas. So we know that when our planets were forming, our solar system had to have had gas. So it wasn't a simple question of, did we get the right level of SLRs from these massive stars? It was also, did the disks even survive? Because radiation from massive stars can also destroy the disks. So we took that into account as well. And our results. So out of all the simulations we analyzed, so we analyzed 10 simulations from each type. So expanding and collapsing, we had 10 simulations, and each simulation had 1,500 stars. So that's a lot of stars to take into account. And we found that 0.2% were enriched to or at least enriched with aluminum to the level of our solar system, sorry, our solar system or above. And I put the results only for aluminum just because the measurement for the solar system value of iron that we had to compare to is not as kind of constrained, like we don't have an exact measurement. So my results for that is a bit more complicated. The aluminum ones I can explain a bit more easily. So in the expanding regions, we found that 0.2% were enriched to the level of the solar system or above. And then in the expanding regions as well, we found that 0.02% were enriched and had enough gas left to form Jupiter and Saturn, if that were to be our solar system. So you can see that it added in that condition of having to have enough gas actually dropped down the probability of finding disks that could actually replicate our solar system. And then the collapsing regions had a bit higher probability just because, as I mentioned, over time, the stars get closer together. So that means these sun-like stars are actually getting closer to the massive stars. So they would receive more enrichment compared to those that are drifting away in the expanding regions. So the collapsing regions, we found that 2% of them were enriched. And then when you add that condition of having enough gas, then 0.1% will enrich the level of our solar system or higher and had enough gas to form Jupiter and Saturn. And these numbers seem very, very tiny, but when you think of it in the context of the fact that our galaxy has hundreds of billions of stars and there's hundreds of billions or trillions of galaxies, that actually leaves a possibility for quite a lot of planetary systems out there to be similar to our solar system. So to me, that's very exciting. I put the numbers down and it seemed like it's not a lot, but when you think of space is huge. So there is a possibility that there are other planetary systems out there like that, but probably not the most common. So what does that have to do with life on Earth? That was the title of my presentation, how exploding stars might have helped the development of life on Earth, and I haven't quite mentioned that yet, so we can get to that. So Aluminium-26 is believed to be one of the dominant heating sources of planets while they're forming. So this picture is actually what we call a magma ocean planet, which is a planet in its very early stages of formation. So how planets form is just smaller planets that we call planetesimals, just smashing into each other, and this actually like releases a lot of heat. But Aluminium-26, going from Aluminium-26 to Magnesium-26 is an exothermic reaction. So that decay reaction also releases heat, and it's believed that that heat being released from those reactions could be the dominant source of heat while a planet is forming. And so that means Aluminium-26 affects how hot a planet gets while it's forming. And that also influences how much water the planet has, because we know that if water gets too hot, it's going to evaporate, it's going to go off into water vapor. So the amount of water we have on Earth could have actually been affected by how much Aluminium-26 we were enriched with like 4.5 billion years ago. And that's where it comes into being related to life on Earth, because we know that if you didn't have any water on Earth, there wouldn't be life, because water is a key ingredient for life. And if you had way too much water, so if you had a very like oceans way deeper than ours, that could also limit the probability of life developing on Earth. So the fact that we had just the right amount of water and just the right conditions for everything else, SLRs could have had a part to play in that. And now because Aluminium-26 is made in massive stars and released by a supernova, we know that during supernova explosions, iron is also released at the same time. So that's why we looked at both Aluminium-26 and iron, because the disk enrichment mechanism says that it's a supernova. So if a supernova happens, it's going to release both iron and Aluminium-26. So that's why I looked at both of them to see if we could find planetary systems that show the levels of enrichment and also keep the same level of gas. So our pale blue dot and the fact that we even exist could have had something to do with SLRs. So just in summary for everything I said, that just finding, analyzing meteorites and finding the magnesium and the nickel in the meteorites, we know that there's evidence that there must have been aluminum-26 and iron-26 very early on in our solar system, just because they don't live for very long. So they had to have come into the disk, and then for them to end up being trapped in the meteorites, they couldn't have come when the planets had already formed, because we see like a very even distribution of them. And it makes sense that when a supernova explodes, if that material encounters a disk, it would be evenly distributed compared to if a planet was already formed. You might not have gotten as even of a distribution, because it would have stuck onto maybe one planet in that position, and there would have been like a lot of empty space. So we know that when the solar system was very young, when it was still lots of gas and dust, there must have been some mechanism by which aluminum-26 and iron-60 got into the solar system. And these isotopes are formed in massive stars. Massive stars explode and release. We know that they release material, but we want to see whether for the disk enrichment theory, we want to see whether that could have been the source of these SLRs. And we care about it because these SLRs, because they affect the water content, or because it's believed that they affect the water content of a planet, it could be another factor to consider when considering the habitability of a planet. So when we're looking at exoplanets, it could add to some of the factors that we look for in our search. And if you know me from Twitter, you know that I love GIFs. So thank you for listening, and that's it from me.
Thank you, Cheyenne, for a very interesting talk. You also have received some interest in the chat, so we have a few questions for you. So first question is from Medina. How do you detect the different atoms and isotopes in stars?
How do you detect different atoms and isotopes in stars? I'm trying to think of, okay. So,
would you do it?
Because it's more than one way that I can answer this question. So, sorry, what were you saying, Claudia?
I was wondering if you did it spectroscopically.
I did. That was a few years ago, actually. Yeah, but yeah, spectra is one way. So each element, I'm trying my best to remember from about 3 years ago. So each element has a kind of a very unique spectra. It's kind of like, they call it like the fingerprint of the element. And when you can look at starlight through a spectrograph, which is what gives you that spectra. So it's just lines that go, it just looks like lines going up and down. And so yeah, like I said, each element has a very unique spectrum. And from looking at that, you can tell what a star is made of, and also from knowing the reactions that go on in stars at the different stages as well. So it's kind of the mixture of the two. I don't know if that completely answers the question. I had to go into the archives of my brain for that one.
Then second question from Olivier Luz. What portion of the heavier elements are made during the massive star's ordinary life, just after the supernova stage? And what portion is instead creating during the supernova event itself?
So for aluminum and iron, they're both made, the majority of it is made while the star is still being a star. Some more could be made during the explosion, but we were looking at, I think the majority of it is made in the star and released as it explodes. But yeah, there are other elements that are made only when the explosion happens, like the heat from the explosion could make other elements, but aluminum and iron are made like while the star is still fusing elements.
Another question from Rachel Oliver. Do your results make you think there is a good chance that life exists elsewhere in the universe, and how common might it be?
So my results on their own, I think definitely reaffirmed to me that life exists somewhere else where it could have existed in the past or may exist in the future. Because there's a chance that there's probably hundreds of thousands, if not millions, of just from the probability of these results, that there are other planetary systems with that level of enrichment. So if that was the level of enrichment that we needed for us to develop life, then we know that there are other planets and other planetary systems with that condition as well. So that definitely makes me think, yeah, it's possible.
Thanks a lot for that. And a question from Liam Rooney. Is decay of Aluminium-26 and Iron-60 the only way that magnesium and nickel are made in stars, or are there other processes?
No, so it's definitely not the only way. Magnesium, I know, is definitely one of the elements that's made during the fusion processes in stars. The thing about the decay from aluminum and iron is just one of the ways that you could get magnesium and nickel. And the reason that they're looking into, like astronomers are looking into that decay process, is just because when you look at the concentration of, or the abundance of magnesium and nickel in our solar system, and then you look in what's called the interstellar medium, so kind of around, it's very obvious that we have more magnesium and more nickel. So it's like there must have been some other process apart from just the normal planetary system processes that added more magnesium and nickel into our solar system. And that's why we ended up looking into where could it have come from, and then knowing that it came from massive stars, then kind of going from there. So there are other processes, but just looking at the abundance, we're seeing that there's an additional process that added to our solar system.
Great. Another question from Medina. Have these isotopes, for example, Aluminium-26, has been found on other planets, or can we find it on other planets?
So looking for specific isotopes in other planetary systems on other planets is extremely difficult, just because of how far away exoplanets are. It's definitely difficult with our technology. But I did, while I was doing kind of my research for this project, I came across one of the papers that mentioned that because the decay heat affects the amount of water on a planet, if a planet has no aluminum-26 at all, it could just be engulfed in a huge ocean, and a very, very, very deep ocean. And that ocean could actually make the planets bigger, because it's kind of water being collected onto the planet. So what the paper was saying was, looking at what we know about planetary planet formation, if we happen to find an exoplanet that's a bit bigger than it's supposed to be, or a bit smaller than it's supposed to be, that could give evidence that it has SLRs. But in terms of actually pinpointing to say, I can see aluminum, that might be a bit more difficult. But we can look at the size of planets in the future and probably be able to tell how much enrichment they have.
Thank you. Question from Idris. Would you say the matter in our solar system came from the same supernova explosion, or maybe there were different supernova events that contributed to the formation of our solar system?
So it's definitely possible, and it's probably more likely that it's multiple supernova events. I would think that, so the material, so the dust that was in our disk when the solar system formed, or was just beginning to form, definitely came from past generations of stars, and more than likely more than one supernova. So, but in terms of the actual isotopes for aluminum-26 and iron-60, that also could have come from multiple, because our simulations, we didn't pinpoint how many supernovae it came from. It could have been 2, it could have been 6. We just looked at the level of enrichment. But it's worth noting that massive stars of that size, and especially in our simulations, we needed stars that exploded within 10 million years. So these are stars that are 20 times the mass of the sun, and the higher up you go, the more rare these stars are. So I think definitely multiple supernova events would have contributed to the material in our solar system now.
Okay, great. We have one last question from Candice, which is, she would like you to share your favorite star or space fact, like something that not many people know, but the thing that excites you the most.
I think my absolute favorite space fact of all time is quite similar to my presentation, actually, but it's the fact that all of the elements, apart from hydrogen, every single element in your body was made in a star. So you came from past generations of stars, fusing these elements, exploding as supernovae, enriching planetary systems. And like that whole cycle to me is just amazing. Just to think like I used to be a star. Obviously, you know, that's my favorite space fact. That's my favorite thing about stars. It's just the fact that everything that makes all of the planets, Earth and everything is just, it was made in a star. And now you're here because of stars. It's amazing.
Yeah, I have to say I'm partial to that one myself. So I don't think there's any more questions in the chat. Your talk was also very well received, and it was a pleasure to have you. So it was great. It was very interesting piece of research that you shared with us. So thanks again. After this, I will hand over to the host again. I just want to thank everyone that connected to for being with us today and listening to these two fabulous speakers. And yeah, see you at our next webinar.
Excellent. Okay, so thank you so much to Dr. Claudia Antolini for chairing this session, and thank you to our two wonderful speakers. I really enjoyed both of your talks. So our next webinar in this series is next week, and we have Dr. Leah Lee, who will be talking about hierarchy, power, and money, overcoming barriers in fundamental experimental physics. So we really hope that you can join us next week as well for this talk. And thank you so much for joining us today. Take care, have a nice evening or whatever time of the day it is where you are. Thanks again. Bye.